Hi, today we're going to do a video on how to find critical numbers and max and mins in problems that have an e to the x. So these are the four problems that we're going to go over. And what I'd like you to do before we get started is actually pause your video and try these on your own, or at least get the derivatives on your own, and we'll go from there. Okay, welcome back with problem number one. So problem number one is a product rule. And when you did that product rule, you should have gotten this derivative. Whenever you have a derivative with an e to the x and a product rule, then you're going to have to factor out an e to the x to set this equal to 0. Before we do that, let's clean it up a little bit. I'm going to rewrite this as 2x to the power of 3, like just move that 2 over, and then e to the 2x. And then I'm going to make this term 3x squared e to the 2x. I mean, even in writing that, we can see that both the first term and the second term have an e to the 2x. So I'm definitely going to factor out e to the 2x. I'm also noticing that both terms have a x to the power of 2. So I'm going to factor out x to the power of 2 also. And what I have remaining now is 2x plus 3. Right? And you can always check. If I multiplied this back, I would have 2x to the power of 3 e to the 2x. And here I would have 3x to the power of 2 e to the 2x. Great. So we want to set this equal to 0. And this is where it's really important to remember your zero product property. A paraphrase of the zero product property says, in order for a times b times c to equal 0, then either a, b, or c must be 0. So if we want this expression to equal 0, this equation, then one or more of these has to equal 0. So let's set x squared equal to 0. Well, x squared equals 0 when x equals 0. So there's one of our critical numbers. E to the 2x. When does e to the 2x equal 0? Well, remember that e is just a number. So if you think of e similar to like the number 3, what exponent could you put on the number 3 that would make 3 equal 0? You really couldn't, because 3 to the 0 gets you 1. If you stick a negative number on it, like 3 to the negative 10, well, then you get 1 over 3 to the power of 10. That's not 0. So there is no exponent that you can stick onto a number that would make that number with its exponent turn into a 0. So e to the 2x can never equal 0. Again, even if x is 0, e to the 2x would be e to the power of 0, which is 1. Okay, and then 2x plus 3, well, that can equal 0 when x equals, let's see, that's negative 3 divided by 2. So there we have our two critical numbers. And then we want to find out which ones of these numbers are maxes and mins. So we can make our first derivative test sign chart. And on that sign chart, I'm going to have negative 3 over 2 and a 0. And this is first derivative test. And I need a test number here. So I'm going to do f prime. You know I love to use like negative 10. You could use negative 2 here. I just want to use a number that's really easy. And here I'm going to use negative 1. And here I will use 1. So f prime of negative 10. One thing to know is that it's actually much easier to use the factored form of your equation. So if I put a negative 1 in here, I would get, of course, that's going to be positive. And actually, e to the power of -2, that's still going to be positive because it's just going to be 1 over e squared. So you know what? No matter what I plug in to the x squared e to the 2x, that part's always going to be positive. And then here, if this is -1, uh, oh wait, -10, I'm sorry. If I plug in a -10 here, I would have -20 plus 3. That's going to be a negative. So that means on this interval, f prime is negative. Let's plug in a -1. So again, the outside is going to stay positive, right? This can't be negative. And then if I plug in a -1 here, I get -2 plus 3. That's a positive. So that means on this interval, f prime is positive. And now let's plug in +1, positive, positive. So that's still positive. So what we have here is we have x equals -3 over 2 is a min, and x equals 0 is not a max or min, but it is probably what we call a shelf point. Because we can see here that f of x is, or that, yeah, so f of x would be increasing, and then it's going to hit 0, and it's still going to be increasing. Okay, but we know because this is a critical number that we have a slope of 0 there. In fact, I couldn't resist showing you the graph of this function because I thought it was super cool. So here's what the graph of y equals x to the power 3e to the power 2x looks like. And so here's that -3 over 2 that we said was a minimum. And then look, when x equals 0, we have a horizontal tangent, but it's neither a max nor a min, right? F of x is increasing. Then after that point, f of x is still increasing. Anyway, I just thought that was a cool graph. Thought I'd share it. So now it's time to go on to number 2. And this was a cool derivative, so I thought I would do it with you. We're going to have a product rule here. And the way I do my product rule is go ahead and keep the first part, and I take the derivative of the second part. The derivative of that is just 1. Then this I'm going to keep. Now I'm going to take the derivative of the second part. And there's no chain rule here, right? Because if I chain that, I'll just get 1 again. So what I can see here, let's rewrite this so it's a little clearer. When you look at it now, it's really clear that we need to factor out an x plus 5. Okay, so I'm sorry, I said that wrong. We need to factor out an e to the x minus 1, right? Because we have that in each term. So I'm going to factor out e to the x minus 1. And that means this term just becomes a 1. And this term just becomes x plus 5. Then you can always double check when you factor out. If you were to distribute, would you get back to where you started? So that would take me back to there. And this would be e to the x minus 1 times x. Oh, good. And let's clean this up a little. That's going to be x plus 6. Okay, remember our zero product property says one or both of these must equal 0 in order to get a product of 0. Well, e to the x minus 1, that can never equal 0. There's no number that I can put here that's going to make e to an exponent ever equal 0. But x plus 6 can equal 0, and that's going to be when x equals -6. So I have my critical number there. And I'm ready to do my sum chart. So here's my first derivative test. I only have one critical number, that's -6. And I have, let's see, this is my first derivative test. I always like to write that. I'm going to test f prime of negative 10 just because I love that. And I'm going to test f prime of 0. Again, I like using the factored version um, to do my first derivative test. So if I plug in a negative 10 here, I would have e to the power of negative 11, which is 1 over e to the power of 11, right? And then I would have negative 10 plus 6, which is negative 4. So on this interval, f prime is negative. And then if I plug a 0 into this equation, I'm going to have e to the 1. That's just always going to be positive anyway. I'm going to have 0 plus 6, which is 6. And that's going to be positive. Right? E times 6 is 17 point something, 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 I believe. And so let's see, this x equals negative 6 is a minimum. And that reminds me, I forgot to mark this earlier as a critical number. Okay, so x minus 6 is a min. I got my answer. Now, what was really interesting about this graph, and I could see College Board using this one, because even if you had a calculator, this minimum is really hard to find by looking. Even if you zoom in, it's really tough to find out that x minus 6 is a min. So you actually need to do this process to get there. Or x equals negative 6 is a min. All right, let's do another one. What do we have for number 3? Good one. Okay, hopefully on your own you took a derivative of this and you got that. And we can't factor anything out here. So let's just set this derivative equal to 0. Add 1 to both sides. What exponent would we have to make e to the power of x equal 1? Well, we'd have to have an exponent of 0, right? Because e to the 0 equals 1. So there's our critical number. In fact, it's our only critical number. So let's make a sign chart with 0 in it. And let's say that we have f prime of negative 1 and f prime of 1. Okay, so let's see. E to the power of negative 1 would be 1 over e minus 1. Uh-oh, what is 1 over e? Well, e is 2.7, so you can kind of round it to 3. So, I mean, e is 2.7 infinite. So 1/3 minus 1, that's going to get me a negative answer. And then here we would have e to the power of 1 minus 1. And e to the power of 1, again, it's 2.7, blah, 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 minus 1. So that's going to be positive. Therefore, wow, everything's ending up being a min, isn't it? Therefore, x equals 0 is a minimum. Okay, one more. Oh my gosh, I love this next one too. And it is another great one that even if you had a calculator, this one on the calculator, you can't really see the max or min. So you have to do the calculus to be able to find it. So, oh, you know what I forgot to write here is we're just going to do this on the interval of, I think I wrote it on the original. We're going to restrict this to the interval of pi over 2, comma 3 pi over 2. And notice it's an open interval because secant is undefined on the pi's over 2's. So basically, let's just look at this graph right in between here and here. Also, tangent that we have in our derivative is undefined there. So that way, let's just look at the defined part. I mean, we could do it on infinity, but this is easier. So what we have here is, I just went ahead and pulled the 2 outside of the whole derivative because I'm going to factor it out eventually anyway, right? E to the x, and then the derivative of secant x is secant tangent. And then I repeated my secant x here, and the derivative of that is e to the x. And then the derivative of e to the x is e to the x. Now, what I like about this is it gives us two situations. When you have an e to the x and a product rule, you're always going to be able to factor it out after you take that derivative. When you have a secant x and a product rule, you're also always going to be able to factor out secant x. So what I'm going to do here is I'm going to factor out the e to the x from both terms and the secant x from both terms. Now, if you had the 2 inside your derivative, you would also factor out the 2 right now. So what does that leave me with here? It leaves me with just a tangent x and a plus 1. Okay, is this going to work out? Well, let's see. Our zero product property says at least one of these things must equal 0. Well, 2 can't equal 0. E to the x can't equal 0. What about secant x? Can secant x equal 0? Secant is 1 over cos. So if secant is 1 over cos, then you're never going to get 0 out of it. In fact, secant x is undefined at those points. And so that's going to leave all this hanging on tan x plus 1 equals 0. Now, when you see these kind of situations, don't panic. What almost always happens is when you subtract and divide, you're going to get some sort of answer over here that you're used to seeing. So this would mean that tan x would have to equal -1. Well, do we have any radian values for which tan can be -1? It's going to be some sort of pi over 4, right? But it's not going to be quadrant 1, but it could be quadrant 2, which is 3 pi over 4, and it could be quadrant 4, which is 7 pi over 4. Now, we're restricted in domain to pi over 2 and 3 pi over 2, so we can ignore the 7 pi over 4. So this is the only critical number that's on our interval, or in the restricted domain of this problem. So let's make our sign chart. 3 pi over 4. This is a first derivative test. I know kind of that I don't want to go past pi over 2, and I don't want to go past 3 pi over 2. So I'm going to have to keep my test values close. Okay, so what can I test here? What is between pi over 2 and 3 pi over 4? 2 pi over 3 is what comes to mind there. And what is it between pi over 4 and 3 pi over 2? Well, I'll tell you what comes to mind there is pi. So let's look at our factored version of the derivative. Well, 2 and e to the x is always going to be positive, right? And so I'm going to have positive, that's 2 and e to the x. And then I'm going to have secant of 2 pi over 3. I don't actually have to figure out this value. I just need to know if it's positive or negative. So this is in quadrant 2, and secant is actually negative in quadrant 2. And then tan x plus 1, so tan of 2 pi over 3 is negative root 3. And negative root 3 plus 1 gets me a negative. So that ends up being positive. I know that the square root of -3 has to be greater than 1, if you're wondering how I got that. So f prime is positive here. So let's check f of pi. So if I look at my f of pi here, then I know 2e to the x is going to stay positive. Secant of pi. Well, cos of pi is -1. So secant of pi, the reciprocal, is also -1. And then tan of pi is going to be 0 plus 1. Careful, don't get excited when you have a 0. It doesn't always make everything disappear. And so I have a positive times a negative times positive. That's going to be negative. So finally, we found a max. X equals 3 pi. Oh, let me scoot that up. X equals 3 pi over 4 is a maximum. And again, this one was really hard to see, even on Desmos, I had trouble finding this max, and I had to use some mad skill to get that into the window. Okay, well, that's it for my video. One, I hope there weren't very many mistakes. Two, I hope it was helpful. And three, I really hope this recorded.